In section 4 of chapter 4, here we look at the different ways that we can more or less represent the outcomes of a sample space using different counting methods. So our focus is to look at finding the total number of outcomes in a certain number of events, and we're going to talk about the fundamental counting rule, a permutation rule, and also a combination rule. So kind of before we get into technical terms, I wanted to kind of re-illustrate the tree diagram approach that we talked about in the first section when we looked at just basic probability and how to find a sample space. So here in this problem, we have a man that has 3 different types of sweaters and 2 different pairs of jeans, and we want to determine how many different ways we can pair these items together. So if we think about the way in which we did the tree diagram, we have 2 different options to make an outfit. We have the 3 different sweaters, so red, blue, or green, and then we have 2 different types of jeans, black and denim. So if the young man decides to wear the red shirt, then he can pair that red shirt with a pair of blue jeans and a pair of black jeans, or denim and black. And then the outcomes, which in this case are the outfits that he can put together, would be the red sweater and the black jeans, or the red sweater and the denim jeans. And this process is going to help us talk about our different outcomes, but also help us get into different counting rules on how we can find the same number of outcomes without having to do this process each time, because it is a bit tedious if we look at more options over time. So if I kind of speed this process up and we look at all the different outfits that we can make using the tree diagram approach, we see that we can make 6 different ways to pair the items together. Now, the benefit of the tree diagram is that we know what the outfits or what the different ways are comprised of. The other methods that we'll talk about in this section, we have no way. We only know the total number of outcomes. We don't know what those outcomes are unless we list them out in some way. So an alternate method in figuring out, or another method in figuring out how many different ways we can pair together items, we look at, well, there's 2 events here really, and those events are that he can have a sweater and then he can have a pair of jeans, right? Those are the 2 events that we're looking at. Now the sweater consists of 3 different options, right? We know that there is the red, the blue, and the green, and then the jeans consist of 2 different options, which is the black and the denim. So another way for us to get the 6 different outcomes is just multiply those values together, and we get 2 times 3 is we get the 6. Now if I did it this method, I don't know what those outfits look like unless I wrote them down, or I could think about it because there's only 6. It's not too difficult. But when we have more events with more options, then the value that we seek will be much larger. Now, in our first little principle we look at, the method in which I'm talking about is actually considered the fundamental counting rule. If we have a certain number of events and each event has a certain number of options or possibilities, then the fundamental counting rule just means that we can multiply those possibilities together. So in this case, when we look at this one, we had 2 different events, sweaters and jeans. Sweaters had 3 different choices, jeans had 2 different choices. So instead of making that tree diagram, I just multiply them together and we can get the same value, 6, which is ultimately the goal, is how many ways can we pair the items together. The question is not really concerned with what is the pairing of the items. So we really don't need this information here. We just need to know how many we can create versus what are the outfits. And so now we can apply that to different types of concepts. So for this example, it says how many 5-digit zip codes are possible if digits can be repeated and if the digits cannot be repeated. So we think about a zip code, the zip code for North Lake College, 75038. There's 5 digits. Each digit is different, So that would be a representation of cannot be repeated, but we do know there are zip codes where the numbers are repeated. So if we think about the first one, I could have a zip code of all sevens, right? 7777, and that is represented, the digits can be repeated. So if we think about this as the fundamental counting principle, which just states that we look at the number of different options or the number of different events that we have, and in this case, each digit represents an event. And then we look at, well, based on those 5 digits, how many options or possibilities lies within each digit. So here, if we kind of look at, well, these are my 5 digits. These are the place markers. So this is the first digit of my zip code, the second digit, the third, up to the 5th. And the first digit can be any number from 0 to 9. So I know that means there's 10 different numbers I can choose for the first digit. Well, since repeats are allowed, that means the second one can be 0 to 9, which is also 10 digits. And the third one can be 0 to 9. The fourth one and the fifth one, they all can be any number from 0 to 9, as illustrated here, because 7 is within each of these intervals. And so each digit has 10 possible choices. So by the fundamental counting theorem, if I know that we have these distinct events, so the 5 digits, and each event has 10 different choices, we can just multiply those together and we get the number of ways that we can form zip codes. And there are 100,000 zip codes we can make by using this process if repeats are allowed. So if we look at the other example, which is now we don't want to allow repeats, and still we have a zip code like North Lake College, 75038. So again, we can use the fundamental counting theorem. It's the same concept, except now we have some restrictions. Now the first digit, it really can be any number from 0 to 9, so we still have 10 options. However, the second digit, if I used the number 0 for my first digit, that means I can no longer use the number 0. So my second digit can be any number from 1 to 9. So now there's only 9 options. And then my third digit can be any number from 2 to 9, which that means there's 8 options. And my fourth digit can be any number from 3 to 9, and then my fifth number, and so on. And so now we look at each time our number of possibilities is reduced, but still we can use the fundamental counting theorem because we have our 5 different events, we have the number of possibilities for events, and so we can multiply that together, and we figure out that now if we limit the numbers that we can choose from, there's only 30,240 possible zip codes that could be created if there's no repeats. And of course we know that there are zip codes that are repeated, and in fact the US has about 40,000 41,000 zip codes that are in use currently. So there's zip codes clearly that do not have repeats, and there are zip codes that do have some repeats. So there's a mixture. We haven't quite reached the 100,000 zip code mark yet. So that was the fundamental counting theorem, and we will apply that throughout, actually, when we talk about permutation and then some with combination as well. So a permutation is the way how we arrange an object a specific number of times. So we have to, and also with the permutation, we consider that the order is important. So the way in which we order something is done specifically a certain number of times. And in this case, we look at, in this formula down here, where n represents the total. So if we look at, we'll look at this example, and r represents the number of ways that we are arranging these events based on a specific order. So in PR, not the radio station, but for permutation, it means n factorial. So this symbol here, if you've never seen it before, is not that we're really excited about the n. It means factorial, so it's a math computation. So for an example, if I wanted to figure out, let's say 5 factorial, we look at successive multiplication from 5 all the way down to 1. So any number that you want the factorial of, it's always going to be that number, and then times 1 less for each value until you get to 1. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. And then you just keep going on. And so the larger this number is, the higher the product, because you're multiplying that number times all the values lower than it. And if we think about the example that we looked at, the last one with the zip codes, it's a true number permutation, because it was, but we can actually use this formula to figure out the same thing that we did with the second example, because it was a specific order in which we were using the numbers. And I'll kind of go back and check that. And then 0 factorial is 1. Mainly we think about the number of ways in which you can arrange something, and there's only one way to arrange nothing, and it's not to arrange it at all. Also 1 factorial is 1 as well. So we will, anytime we talk about an arrangement of objects where there is a specific order, we will utilize this formula. So for an example, it says how many 4-letter permutations can be formed from the letters in the word decagon. We first think about how many objects or how many events are there that we have to choose from, and the word decagon has 7 different letters that we want to be able to choose from. And from that 7, we really only want 4 letters. So that represents our R, because we are choosing 4 of these letters to form a new word. And then in this case, order is important because we want different words. We don't want the same word. So we're concerned with the way in which the words are ordered. So if we kind of set up the our formula here, I have 7PR, and based on the formula, that's 7 factorial divided by 7 minus 4 factorial. And I like to simplify this, so that becomes 7 factorial divided by 3. And if I utilize, this notion up here, the 7 factorial, I can expand that out as 7 times 5 all the way down to 1. And then 3 factorial, I can also expand that out as well as 3 times 2 times 1. And then I look in the numerator and the denominator, and I determine, well, since this is multiplication, I can easily eliminate some of the value, because anytime I have a number like 3 divided by itself is just 1, so I can cancel those out. And then really we're multiplying 7 times 6 times 5 times 4, which is 840 ways that we can really arrange the letters in decagon to form different words. And those words, they may or may not be real words, but they're different words. So let's say we wanted to do the calculation a little differently. You don't have to actually use this expanded out process. You can input that information into Desmos. So if I go over here and I did 7 factorial, exclamation point, and then 3 factorial, it gives you the same value. So it knows that the exclamation point means to multiply, and so it will give me that number. The same thing is true for the calculator. So if you have downloaded the TI-84, you'd have to hit 7 and then go to the math option, look for PRB, which is probability, and then it's number 4, and that'll give you 7 factorial. But you can also divide them. So it's math number 4 divided by 3, and then math PRB. So this is a little more cumbersome than the Desmos, but you can still do it in here, and you get the same answer as well. So let's look at another example, and I want to explain this example 2 different ways. So we look at how many different ways can a researcher select 5 rats from 20 and assign each a different task. We have to consider that although in the examples for permutation, so we know order is important, but why is it important? So here the statement that they're assigning each rat a different task implies that the way in which the rats are being assigned to the different test is important. So if I have 5 different tests, that means if you have rat A can be assigned to test 1 or test 2 or test 3 and so on, and then that different assignment represents a new order. So it's very specific. if they were taking the same test, so if there were 5 tests and those 5 tests were all test A, then it wouldn't matter. Then rat 1 could take any one of the tests and it would still be the same information because they're all the same. But because the tests are different, that means orders implied. And so we look at, well, 20 is the total because there's 20 of, the rats to choose from. And then we only really want 5 of them. So how many ways can we make this assignment based on the 20? And so that's the number permutation. And we just set up the formula. So 20 factorial divided by 20 minus 5 factorial. And we can expand it out like we did before. So in here, I don't want to, unlike the last time I wrote it out because it was smaller numbers, but I really don't want to write this all the way out to 1. So because the denominator is 15 factorial, instead of me writing this all the way out to 1 and then having 15 and writing that all the way out to 1, I can notice that I can stop at 15 because that's the number in the denominator, 15 factorial and 15 factorial, and those will eliminate, and I'm just left over with 20 times 19 times 18 times 17 times 16. And if we kind of consider that, this information here, this is the same as what we looked at kind of in the beginning. The information is the same because we have, well, I'll explain it here a little bit. But if I multiply that together, we get 1,860,480 different ways to assign 5 rats to a different test from 20 rats to choose from. And again, I can easily calculate that in either Desmos, so 20 factorial divided by 15 factorial, so I get that value, or we can even do 20 times 19 times 18 times 17 and then times 16. So multiple approaches here to do the numerical calculations. Now, another way to look at this is we could also think about the fundamental counting theorem. Because of the problem, we have 5 different tests. So the first test, I can choose any of the 20, right? Doesn't matter which ones I choose, I can choose any of the 20. Once I've chosen one of them, they're taking the first test. And then for the second test, I can choose from any of the 19, and then from the third test, I can choose any of the 18, and so on. From the fourth and the fifth test, I have 17 and 16 to choose from. So when I had expanded out the previous problem, and the only thing that was left over was this, 20 times 19 times 18 times 17 times 16. So anytime we have a problem that involves a permutation, we can also think about the fundamental counting rule at the same time, and it will arrive at the same answer. So for our last example for permutation rule, says how many different ways can 4 tickets be selected if 50 tickets from 50 tickets if each ticket wins a different prize. So we think about the different prizes. This is what makes it a permutation in the order specific, because those different prizes would mean the difference, probably what type of prize you receive. If we have a grand prize versus first place runner-up, and then second place runner-up and third place runner-up, those are definitely 3 different prizes. We could have $1,000 prize, $100 prize, a $10 prize, and a $1 prize. So that different order leads us to believe, or those different prizes leads us to think of number permutation, because this in which the order matters. If I'm the grand prize winner, I'm going to like that a lot more than if I was the third place runner-up prize winner. So that already, I could either take this spot, or I could take this spot, or this spot, or this spot. So that represents just me alone 4 different ways of winning a prize. So when we set this up, 50p4, 50 factorial divided by 50 minus 4 factorial, which is 50 factorial over 46 factorial. You could stop here and just evaluate this in Desmos with a calculator, or if you want to do it by hand, you could expand it out, stopping at 46 factorial because that's what's in the denominator, and then we just have that left to multiply, and that's just like the fundamental counting theorem. And so there are over 5 million different ways that 4 tickets could be selected from 50 tickets, since the order is important. So now we switch gears and we want to talk about the combination rule. Here we look at now, order is not really important with the combination rule. We don't really care in which the way the items are selected. So the formula looks very, very similar for NCR, which is the C denotes a combination. We still have n factorial. It's still divided by n minus r factorial, but there's an additional r factorial in the denominator, and it's just eliminating all those options where the order was important. So now we look at less specific outcomes, and these values are generally a lot smaller when we calculate for a combination. So in this example, it says DVD selection. How many ways can a person select 5 DVDs from 8? It really doesn't matter how we select the DVDs. It's not, so here I have 8. So if I selected, let's say we just selected the first 5 DVDs, and then in this particular order, right? This one first, this one second, this one third, this one fourth, this one fifth, and then I selected the same 5 DVDs, but I chose the Madagascar one first, and then I chose the Croods second, and then the Guardians third, and Turbo fourth, and Peabody and Sherman fifth. Then even though I selected them in a different way from the first selection, it's still the same 5 DVDs, and they count as one because I don't care about the way in which I chose them. As long as I'm always taking those 5, it will only ever count as one, regardless of the order they're in. If I was concerned with, I want this one first and this one second, then I can look at these 5 DVDs counting for many different ways to choose them because of the order. But since I don't care about the order, as long as these 5 are contained, then the order is not really important. We still want to be able to identify the value for R, so how many objects are we selecting, and the value for N, which is the total that we're choosing from. And so for this one, very similar setup. We have 8, choose 5, so 8 factorial over 8 minus 5 factorial divided by 5 factorial. We can simplify that as 8 factorial divided by 3 factorial times 5 factorial. And then I still like to expand it out. So in the denominator, we have some choices now. Since there's 2 numbers, I can either write this all the way out to 3 factorial, or I like to write it out to the bigger number, which is in this case 5 factorial, and then I can eliminate the 5 factorial, and I can expand that out even more, and I know that 3 factorial is just 3 times 2 times 1, which is the same thing as 6, so that gets eliminated, and then so I can get it down to just 2 numbers, 87, which is a little easier multiplication than thinking about, what's 8 factorial divided by 3 factorial times 5 factorial. It's still, we can evaluate this here. If we look at 8 factorial divided by 3 factorial times 5 factorial, so 56. And the other thing we can also look at is the proper way in which to enter it into the 84, because if I type in, let me show you here. So 8 factorial divided by 3 factorial and then 5 factorial. So if I don't use parentheses, then it will give me a much larger number than I would expect. So we have to group the numbers in the denominator together in parentheses so that the calculator can only follow your instructions. So there we go. You can also enter a stacked fraction too. I think it's alpha and y equals, so number 1, and then you can input it that way as well as kind of like a stacked fraction. Okay. So see, we look at a reduced number of ways because we don't care about the order. Only 56 ways for us to select 5 from the 8. So let's look at a different assignment, a different example that we can work 2 different ways. So how many ways can an advisor choose 4 students from a class of 12 if all are assigned the same task? And then how many ways can the students be chosen if they are each given a different task? So we have to consider same task versus different task. which one's a permutation, which one's a combination. So we think about first we think about the value of r, so we're choosing 4, so r is 4, and then the value of n is 12. The same task would indicate that we don't care how we pick the students. They're all doing the same thing. So it doesn't matter if I'm picked first or someone else is picked first, we're all doing the same thing. So that would be a combination, so NCR. A different task would mean that the task, if there's 4 different tasks, then I can be chosen for task A, I can be chosen for task B, or I could be chosen for task C and D, and then each different task I'm chosen for is a different outcome. So that one we look at NPR. So for the same task, it's a combination problem. We set that up, 12C4, and then we just set up the formula, and we go through and we evaluate how many ways can that occur. So again, I always like to show expanding it out and kind of how I can get that answer without using the calculator, but then I also show the calculator as well. So you can see here that I'm working through first, I expanded it out to 8 factorial, so I know that I want to eliminate the 8 factorial in the denominator. And then when I wrote it out in the denominator, I expanded out the 4 factorial, where I know 4 times 2 is 12, so that can be eliminated. And then 2 can go into 10 5 times, and really the multiplication is 11 times 5 times 9. But ultimately, you could just stop here and then evaluate this in Desmos or in the calculator. That would be fine as well. But there's 495 ways to assign 4 students to the same task when you have 12 students to choose from. When we look at a different task, so 12P4, now we actually care about the order. So we have 12 factorial divided by 12 minus 4 factorial. So 12 factorial over 8 factorial, expanded out to 8 factorial like before. We're only crossing out the 8 factorial. And this is like the fundamental counting theorem was left over. So now there's over 11,000 ways to assign 4 students from 12 students when the task is different. So that's the main difference between a combination and a permutation, is the size of the outcome, one, and then the process, more or less, it appears to be the same, right? We're essentially doing the same thing, but I can also get this same answer by using the fundamental counting rule. Because if I have 4 tasks, that means the first task, any one of the 12 students can do it. The second task, if I chose one of the 12, only 11 can do that one. The third task, after I choose someone for the second one, 10 are left, and then the fourth task, 9 are left. So I can also use the fundamental counting, we can also use the fundamental counting theorem here, where for a combination we couldn't. And then for our last example, this problem we have 2 different events that are going on. So how many ways can a person select 6 candy bars from a list of 10 and 6 salty snacks from a list of 12 to put in the vending machine? So we think about where there's 2 different events really. We have a certain number of candy bars, we have a certain number of salty stacks that are going into the vending machine. And really we have to think about, we need to really determine how many ways can we pick candy bars? How many ways can we pick salty snacks? So this is going to be a combination of different things that we've talked about, utilizing the fundamental counting theorem and also using a combination, because it doesn't really matter how we choose the candy bars to put in the machine. That's not really important, but the number of ways in which I can choose the candy bars would be 10 choose 6, right? Those are all the different ways to pick 6 candy bars from 10. And then the number of ways to choose salty snacks would be, well, there are 12 salty snacks and there are 6, so 12 choose 6. And because of the fundamental counting theorem tells us we have 2 different events, so candy bars and salty snacks, and then this represents the number of different options in the candy bars event, and this represents the number of different options in the salty snack event. I just multiply those 2 numbers together, and then that will give us the total number of ways to choose 6 candy bars from 10 and 6 salty snacks from 12. We also can remember that from before, and tells us also to multiply. But this calculation, so this 10 choose 6 is 210, so I'll leave that formula set up for you, and also the 12 choose 6, I'll leave that formula set up to you to confirm that it's 924. But if I multiply those together by the fundamental counting theorem, we get 194,040 ways to do this.